Colorado River is usually described as a water story. It supplies cities, supports farms, crosses political boundaries, and connects Lake Powell with Lake Mead. But stored water does something else before it moves downstream. At Lake Powell and Lake Mead, elevation is also part of an electrical system. The height of the water helps create the pressure that drives turbines inside Glen Canyon Dam and Hoover Dam. In other words, the same reservoir can be both a water reserve and part of a power plant. Both dams are still operating as power plants. This is not a story about a shutdown that has already happened, and it is not a countdown to a date that engineers claim to know. It is a story about operating margin, how much room remains between a reservoir's measured elevation and the physical thresholds that change what its machinery can do. On July 28, 2026, a provisional Bureau of Reclamation table reported Lake Powell at elevation 3,522.73 feet. On July 29th, a separate automatic report showed Lake Mead near elevation 1,041.1 feet in the available early morning readings. Reclamation warns that the Mead report is automatic and has not been checked for errors. Those readings matter because neither dam produces electricity from water alone. It produces electricity from moving water under pressure, and that pressure depends partly on elevation. A reservoir can therefore be read in two ways at the same time. From the surface, it is stored water available to a managed river system. From inside the dam, that same surface establishes part of the vertical distance between the reservoir and the turbines. One measurement belongs to both stories. So the central question is not simply whether the Colorado River contains water. The question is how a system built to store, release, and divide that water behaves as its physical margin becomes narrower. To answer it, we have to follow the water from reservoir to turbine, from turbine to transmission line, and from dam to the farms, cities, tribal nations, and other users connected to the river. A hydroelectric dam begins with a difference in height. Water stored high behind a dam has potential energy. When that water is sent through an intake and down a large passage called a penstock, gravity accelerates the flow. The moving water turns a turbine. The turbine turns a generator. The generator converts that mechanical motion into electricity, which then enters the transmission system. The useful concept is hydraulic head, the vertical difference that helps create pressure across the turbine. More head generally gives the machinery more energy to work with. Less head means the same volume of water reaches the equipment under different physical conditions. That is why installed capacity and actual generation are not the same number. Installed capacity describes what a plant's generating units were designed to provide under specified conditions. Actual output changes with water availability, operating decisions, maintenance, and hydraulic conditions. Glen Canyon Power Plant has 8 generating units with a combined installed capacity of 1,320 megawatts. Reclamation describes the plant as 79% of the total capacity of the Colorado River Storage Project power resources. In an average year, agency material places Glen Canyon generation at roughly 4.5 to 5 billion kilowatt hours. That electricity is distributed through the Western Area Power Administration to customers in Wyoming, Utah, Colorado, New Mexico, Arizona, Nevada, and Nebraska. The value of the power also extends beyond electricity sold at a meter. Reclamation says hydropower revenues help fund operation, maintenance, and environmental programs connected to the federal Colorado River power system. So when reservoir elevation changes, the effect is not confined to the water surface. It changes the physical conditions under which a public power asset operates. It can affect how much electricity the plant can produce, how flexibly it can respond, and how much revenue the system can generate for work connected to the river. The machinery makes the relationship visible. Water enters through structures built at fixed elevations. Penstocks cannot move upward when the reservoir moves downward. Turbine designs have operating ranges. Generators have rated capacities. The transmission system receives whatever the plant can produce under the conditions that actually exist. This is the first reason falling water is more complicated than a shrinking lake. The shoreline is only the visible part. The deeper consequence is a change in the energy available to the machinery below. Engineers describe several elevations around a reservoir, and those numbers are easy to confuse. At Glen Canyon Dam, full pool is elevation 3,700 feet. Dead pool is elevation 3,370 feet. Between those two numbers is another threshold that matters specifically for electricity: minimum power pool. Reclamation identifies Glen Canyon's minimum power pool as elevation 3,490 feet. That number is tied to the physical location of the penstock intakes. Below that elevation, water cannot be released through the power plant penstocks. Minimum power pool is not the same as dead pool. It is not the elevation at which every form of water movement becomes impossible. It is the point at which the normal path through the power plant is no longer available. Hoover Dam has a different design and a different set of thresholds. It has 17 hydropower turbines, including 5 wide head units. Reclamation says all 17 units can generate down to elevation 1,035 feet. From 1,035 feet to the estimated minimum power pool at 950 feet, only the 5 wide head units can continue operating. That means the loss is not all or nothing. Reclamation estimates a 70% loss of total Hoover generation capacity below elevation 1,035 feet. The remaining wide head units extend the operating range, but they do not preserve the plant's full generating capability. These are engineering thresholds, not forecast dates. A reservoir reading tells us where the water was measured on a particular day. A minimum power pool tells us something about the fixed geometry of the dam. Neither number by itself tells us exactly when a threshold will be crossed. Future elevation depends on inflow, releases, weather, operating rules, and decisions that are not fixed by one snapshot. This distinction matters because dramatic language often compresses several different questions into one. Can the dam generate today? How much can it generate? How much hydraulic head is available? Which units can still operate? Can water continue moving through another outlet? When might the reservoir reach a particular elevation? Those are not interchangeable questions. The responsible conclusion is narrower. As a reservoir approaches an engineering threshold, operators have less physical margin. Output can decline before the final usable turbine stops. Flexibility can narrow before the power plant reaches minimum power pool. And the consequences can begin before a headline can honestly say that generation has ended. Lake Powell shows why a dated measurement and an engineering threshold have to be read together. On July 28, 2026, Reclamation's provisional table reported Lake Powell at elevation 3,522.73 feet, with storage of 5,415,182 acre-feet. Glen Canyon's minimum power pool is elevation 3,490 feet. The arithmetic difference was about 32.73 feet. That is a measurement of margin on one date. It is not a prediction that the reservoir will cross minimum power pool, and it does not provide a deadline. It simply places the reported water surface in relation to the fixed elevation of the power plant intakes. Another reclamation status update described Lake Powell at elevation 3,525.17 feet at the end of June 2026. Storage was 5.60 million acre-feet, equal to 24% of live capacity. The same update shows why a reservoir story cannot be told with elevation alone. June 2026 unregulated inflow to Lake Powell was 306,000 acre-feet, or 12% of average. The July 1st median forecast for total unregulated inflow during water year 2026 was 3.50 million acre-feet, 36% of average. These figures describe a weak inflow year. They still do not tell us a certain future elevation. A reservoir is managed through inflow and release, and operations are governed by rules as well as hydrology. For water year 2026, Reclamation says Lake Powell operates in the mid-elevation release tier with an annual release volume of 6.0 million acre-feet. That release number belongs to the operating framework for the year. It should not be confused with a forecast of where the reservoir must finish. Glen Canyon's electrical role also has more than one dimension. The plant has 1,320 megawatts of installed capacity, but installed capacity is not a report of what it generated in 2026. The official sources reviewed for this draft did not provide a complete plant-specific 2026 total. Reclamation's longer-term material says the power plant produces roughly 4.5 to 5 billion kilowatt-hours in an average year. That is an average, not a substitute for a current annual output figure. The plant can also provide short-lived regulation and reserve response. In its July 17, 2026 status update, Reclamation says it maintains 30 megawatts of generation capacity in reserve for system emergencies. This is one reason hydropower can matter beyond its annual energy total. Operators can change water through turbines and adjust generation within the limits imposed by the river, the reservoir, the equipment, and the operating rules. But that flexibility is not independent of elevation. The fixed intakes remain at 3,490 feet. The reservoir reported on July 28 was about 32.73 feet above that line. The system was still operating, but the measured distance between water and threshold was finite. The strongest conclusion is not that failure is scheduled, it is that operating choices become more consequential when the physical margin is smaller. Lake Mead presents a similar problem with a different machine. On July 29, 2026, Reclamation's automatic Lower Colorado report showed Lake Mead near elevation 1,041.1 feet in the available early morning readings. The agency warns that the automatic report has not been checked for errors, so the figure must be treated as provisional. Compared with Hoover Dam's estimated minimum power pool at 950 feet, that reading was about 91.1 feet higher. But the more immediate engineering threshold was not 950 feet. It was 1,035. All 17 Hoover turbines can generate down to elevation 1,035 feet. Below that level, only the 5 wide-head units can continue toward the estimated 950-foot minimum power pool. The July 29th reading was about 6.1 feet above the 1,035-foot all-unit threshold. Again, that difference is arithmetic, not a forecast. It does not tell us when the reservoir will move below the line or whether it will. It tells us where one provisional reading stood relative to a known engineering threshold. This is where the phrase, "the dam is still generating," can hide an important change. A power plant does not have to lose every turbine before lower elevation matters. Reclamation estimates that Hoover would lose 70% of its total generation capacity below 1,035 feet. That is a capacity change, not a claim that the regional grid automatically goes dark. The Colorado River is one part of a much larger power system, and the locked evidence does not support a specific blackout prediction. The 5 wide-head units are not an additional power plant waiting below the other machines. They are part of Hoover's 17-unit fleet. They're wider operating. Range means some generation can continue after the other 12 units leave their supported range, but the plant would be operating with a much smaller set of machines. It also does not support a precise statement about Hoover's available megawatts at the July 29th elevation. That would require a dated operational source connecting current conditions to current machine availability. What the evidence does support is a clear sequence. Lower water reduces hydraulic head. The plant's operating conditions change. At 1,035 feet, the number of turbines able to continue generating falls from 17 to 5. The system reaches estimated minimum power pool at 950 feet. This sequence makes Hoover a better example of narrowing capability than of a single on-off switch. Long before the final threshold, operators may be working with less generating capacity and less room between the reservoir surface and the next physical constraint. Power is only one demand placed on stored Colorado River water. After water passes a dam or is released downstream, it remains part of a delivery system. Canals, aqueducts, pumping plants, reservoirs, and other infrastructure move water toward the people and landscapes connected to the river. This creates a basic physical tension. Water held at elevation can contribute hydraulic head. Water released can pass through turbines and produce electricity, but it is also moving through a system governed by delivery and operating obligations. The same acre-foot cannot be treated as if its power value and its delivery role belong to separate rivers. The current framework is not one document written for one purpose. Reclamation describes an operating structure that includes the 2007 interim guidelines, the 2024 near-term supplemental environmental impact statement record of decision, and the 2026 annual operating plan. Those rules sit over a physical network whose purpose extends far beyond generation. Reclamation says the Colorado River supports about 40 million people, 30 tribal nations, and 5.5 million acres of farmland. The system also crosses 7 U.S. basin states and includes obligations and users in tribal nations in Mexico. It is not a single-state reservoir account, and it cannot be reduced to a contest between one city and one dam. That scale changes the meaning of an operating decision. A release can affect reservoir elevation and the head available to a power plant. It can also be connected to downstream management in a system responsible for water deliveries across an enormous region. Holding more water at elevation is therefore not a decision made for power alone, just as releasing water is not a decision made without regard to the reservoir. Each action takes place inside a framework that must account for several functions at once. Hydropower revenues add another connection. Reclamation says those revenues help fund operation, maintenance, and environmental programs associated with the federal power system. Reduced generating opportunity can therefore matter not only as an energy quantity but as part of the financial structure that supports the system. None of this means there is one simple exchange rate between water and electricity. The locked evidence does not say that 1 acre-foot released creates one predictable consequence for a household bill, a farm, or a city. The defensible point is more structural. The reservoirs, power plants, canals, and delivery obligations are parts of the same managed river. When hydrology reduces the margin available at the reservoirs, the system does not get to solve the power question in isolation from the water question. The scale of the Colorado River system makes simple blame attractive and misleading. Reclamation says the river supports about 40 million people, 30 tribal nations, and 5.5 million acres of farmland. Its users and obligations extend across 7 U.S. basin states, tribal nations, and Mexico. Those categories are not interchangeable. A city water system is not the same as an irrigation district. A tribal nation is not simply another municipality. A power customer is not identical to a farm. Mexico is part of the international river system, not an 8th U.S. state. Each relationship has its own legal, physical, and institutional context. That is why the question, who uses the water, cannot be answered honestly with one villain. The archival images in this section were recorded in Imperial Valley in October 1954. They show the long physical connection between diverted water and agriculture, but they do not show current irrigation technology, current labor, or current operating policy. The date matters. Historical footage can explain how deeply water infrastructure has been built into the economy of the region. It cannot prove how a farm operates in 2026. It also reminds us that present obligations sit on top of infrastructure and patterns developed across generations. The images are useful as history, not as evidence that present-day users, equipment, or allocation rules are unchanged. The same caution applies to cities and tribal nations. Generic urban footage can illustrate that millions of people depend on the system, but it cannot show the terms of a current allocation decision. Generic footage of people, homes, or canals cannot be labeled as a particular tribal community without direct provenance. The numbers describe the breadth of the obligation. About 40 million people, 30 tribal nations, and 5.5 million acres of farmland. They do not tell us that every user receives the same amount, has the same priority, or experiences the same risk. This complexity is not an excuse to avoid decisions. It is the reason decisions are difficult. When reservoir levels are lower, the physical system has less margin. But the network of users does not disappear. Water still connects power plants, deliveries, agriculture, cities, tribal nations, environmental programs, and international obligations. Any rule for operating the reservoirs has to confront that whole system. Protecting one function can change the room available for another. Preserving elevation for hydropower cannot be discussed as if downstream obligations do not exist. Releasing water cannot be discussed as if reservoir elevation has no effect on power. The choke point is therefore not one canal, one farm, one city, or one turbine. It is the need to keep many different obligations inside one constrained physical margin. The rules governing the Colorado River are themselves approaching a transition. The present framework includes the 2007 Interim Guidelines, the 2024 Near-Term Supplemental Environmental Impact Statement Record of Decision, and the 2026 Annual Operating Plan. On January 9, 2026, Reclamation released a draft environmental impact statement for operations after 2026. It evaluates 5 alternatives: no action, basic coordination, enhanced coordination, maximum operational flexibility, and supply-driven. As checked on July 30th, the official post-2026 page still identified the draft EIS as the current activity. Its public comment period had closed on March 2nd, but the page did not announce a final operating rule. That final sentence is essential. A draft presents choices for analysis. It does not make one of those choices the operating rule. Until the process advances, the alternatives cannot be narrated as a settled policy. The engineering problem remains even while the policy process continues. Glen Canyon's power plant intakes remain at elevation 3,490 feet. Hoover's 17 turbines do not all have the same operating range below 1,035 feet. Hydrology continues to affect reservoir elevation, releases, and the head available to the power plants. The wider national context is also variable. The Energy Information Administration forecasts 259 billion kilowatt-hours of U.S. hydropower generation in 2026, about 6% of total U.S. generation and still below the recent 10-year average. That forecast does not make the Colorado River responsible for the entire national hydropower picture. It reinforces a more general fact. Hydropower output changes with hydrology. For the Colorado River, the next operating framework has to address a system that serves about 40 million people, 30 tribal nations, 5.5 million acres of farmland, 7 basin states, and Mexico, while also supporting federal hydropower. There is no locked evidence for a single deadline when that system fails. There is no support for saying that Hoover or Glen Canyon is about to stop generating. The evidence also does not make any specific downstream outcome or future reservoir path certain. What the evidence shows is more sober and, in some ways, more difficult. The physical thresholds are real. The dated reservoir measurements are real. The weak 2026 inflow figures at Powell are real. The competing functions of water delivery and power generation are real. And the rules for the period after 2026 were not final as of the July 30th status check. The Colorado River's power problem is therefore not one dramatic moment when everything turns off. It is a narrowing range of choices inside a system that must continue moving water and producing power under uncertain hydrology. The dams are still generating. The river is still serving users. But every foot of operating margin matters more when so many different systems depend on what happens between the reservoir surface and the machinery below.